Good afternoon, everybody. I'm going to make a quick video here about the next topic that we need to do problems about, which is electrical current and resistance. The way we're going to define electric current conceptually is, as it says right here, it's a net flow or transport of charge. The word net there is actually important because if you have, like, I don't know, a flow of like the current in a river, there is plenty of charged particles in a river, but they are all moving together in the same direction. And so as far as charge goes, there's no net charge flow. If you had only positive particles moving, or only negative particles moving, or if they were moving in opposite directions from each other, those would all be net charge transport. But if you just have like regular neutral matter moving along, that does not count as an electrical current. Mathematically, it's going to look like this. The symbol I is used for the intensity of the current, but usually we just call it current. And so the strength or the magnitude of that current, the intensity of it, is equal to the derivative that I have written there, dq dt. So it is the rate at which charge is being transported. The SI unit for it is called the ampere. Usually people just call it an amp. And the symbol for an amp is a capital A. And as you could guess from the formula, an amp is 1 coulomb per second. You may remember that coulombs are a lot of charge, so consequently an amp is actually kind of a lot of current. You have some devices in your house that will use as much current as like an amp at a time, but most electrical currents in our systems are much smaller than that. So like milliamps, for example, are pretty common. And then the other thing that I have noted there in parentheses is that we define the direction of a current's flow based on positively charged particles. When it comes to the current that flows through a wire, there are not any positively charged particles that are moving, because the positive particles in a wire are the atomic nuclei, and they just kind of chill out while the electrons move. But in a fluid, like, you know, a salt solution full of ions, or a plasma or something like that, both the positive and negative particles can move. But regardless of what is actually moving, the direction of the current that we define is the direction that positively charged particles do or would move. So that's going to be the opposite of the direction that the electrons are going. It's rare that that matters, and unless a text or a question explicitly mentions electrons, the direction that they want you to think about is always this conventional direction based on positively charged particles. Now, I've got a couple of other current-related rules written here. In the middle is this idea that if you send a bunch of current into some space, the same amount of current is probably going to come out. The only case in which that wouldn't happen is if you are increasing or decreasing the amount of charge within that space. So like I have this mystery box drawn. I'm sending a total of 8 amps into it. If I know that the charge of the mystery box is constant, then that means 8 amps have to be coming out also. They might be coming out in some different combination. It's not necessarily the same 2 and 6, but the amount coming out has to be the same as the amount going in. Unless, again, unless the mystery box has a changing Q value. When it comes to like a capacitor, then that is part of the deal. The way you charge up a capacitor is you send in current, No, wait, I'm lying. Even when you are charging a capacitor, current still flows out of it. So, yeah, basically you can just think of this as being always the case, essentially. This will come back, this idea will come back when we start analyzing circuits in more detail. It's one of Kirchhoff's rules. You might remember Kirchhoff's rules from honors physics. And then the one idea that we're going to see this year that you did not have in honors physics was the notion of a current density. The idea here is that if you have a wire with a certain cross-section, probably a circle, current flows through the entire space of that wire. So at any point on the cross-section, there should be, charged particles moving. Most of the time, we're just going to kind of pretend that you have the same amount of current at every point on that cross-section, but it doesn't have to be the case. Occasionally, you'll see something like this illustration at the bottom, where the current is more intense in the middle than it is near the edges. That's a more realistic way of thinking about how the charge actually moves through the wire. And so we express that in terms of this quantity J, which is called a current density. So it has units of like amps per meter squared. And there are two basic ways in which you might have to make use of this. If they just talk about the average current density, or they tell you it has a constant current density, then you can just think about these lower forms here. Like the total current would be the density times the area, if it's uniform. If the current density is not uniform, then the total current is going to be based on an integral like this. And that's very akin to a lot of the other integrals you've done for things that have varying density. So I'm not going to do an example of that right now, but you'll see some in the problem sets. The other thing I want to point out, since I'm staring at it, is that current density is a vector quantity, but regular current is not. Notice I did not put vector signs on any of these capital I's. And that's because it doesn't follow vector addition rules. Like if I have 1 amp coming from the left and 1 amp coming from the right, and then they meet, and then there's like an output channel going up. So there's 2 amps going up. 2 amps come in, 1 from each side, 2 amps go out. I would not be able to write that with a vector equation because like the components of those vectors don't work out, right? I can get that result, 1 amp plus 1 amp equals 2 amps, regardless of the angles that I bend the wires at. So current is not a vector, but current density is, because it's related to the the orientation of the cross-sectional area. And so there's an area vector there, just like the area vectors we saw with flux. And frankly, you can think of this as being like a charge flux. It's essentially the same thing. Okay, so that's current. Closely related idea is resistance. Mathematically, this formula right here is your definition for resistance, V over I, or delta V over I. Conceptually speaking, this is the ratio of the potential difference that you apply across some object to the amount of current that flows through that object. And from the formula, you can see it's like volts per amp. So it tells you how many volts do you need to get 1 amp. How many volts for each amp of current that you get. The SI unit for this is called the ohm. The symbol is a capital omega. And as you can see from the formula, that is a volt per amp. This particular equation, people usually rearrange it to be delta V equals I times R, or sometimes just V equals IR. And also, people will often call that equation Ohm's law. It's not exactly correct. Ohm's law is related, but not really the equation itself. But lots of people are going to call it that. So you need to be able to recognize that if someone mentions Ohm's law, they probably mean that equation. But the equation is really just this definition for resistance. Okay, so that definition applies like over an object, basically. If I give you a particular piece of wire or something like that, you can measure what's the potential difference across the wire, how much current flows through the wire. You can calculate the resistance of that object. There is an infinitesimal version of that. So instead of applying over this interval in space, it applies just at a single point in space. And that's this equation here. Rho equals E over J. E is the electric field. J is the current density. And rho is a quantity called resistivity. And you would have seen this last year also. Resistivity is a material property similar to density or specific heat or thermal conductivity, etc. It's something that you would like look up in a table somewhere. What is the resistivity of aluminum? What is the resistivity of copper, etc. I jammed into the corner here. I want to draw your attention to this. That resistivity is not actually a fixed constant value, even for a given material. It's a function of temperature, like density is, for example. You know, if you look up the density of something in a chemistry handbook, it'll tell you the density at a particular temperature. And resistivity is the same way. So the hotter an object gets, the larger its resistivity becomes. So it's easier to send current through cold stuff than hot stuff, basically, for that reason. So if we take this resistivity formula, this is basically the definition of resistivity, and I'm going to do a couple of steps of algebra with it here below. Electric field, I can write as delta V over L. That's a script L, a lowercase script L that represents the length of like a wire or something, the length of an object. The current density J is the current divided by the area. I'm doing kind of like average values here, I guess. But current density is current per area. So that's my first step. I move the L down to the bottom, I flip the A up to the top, gets me to here. But then I'm looking at this delta V over I. That's the same thing as R for resistance. And then I rearrange to solve for big R. That gives me this formula here. This is a formula that you would have seen in honors physics last year, although they would have gotten to it in a different way. But this is another way of thinking about the resistance of an object. So we have these two different resistance formulas here. The first one is about the electrical behavior of the object. It's about how much voltage are you putting on it, how much current are you getting through it. And the lower formula is about the physical properties, not electrical properties, but physical properties. It's about the length of the object, it's about the cross-sectional area of the object, and then this material property, the resistivity, that like you would look up. That second formula is very similar, functionally speaking, to this capacitor formula that you have some practice with also. In that capacitor formula, you need to know the dielectric constant of the stuff between the plates. You need to know the area of the plates, the distance between them. Those are all physical properties that you can use to calculate a capacitance. So this resistance formula is the same way. If you know these measurements for the object, you can calculate what the resistance should be. And using similar reasoning as we did with capacitors, we can think about what would happen with series combinations of resistors and what would happen with parallel combinations of resistors. So I can see from this formula that the longer my resistor gets, the bigger the resistance is going to be. So if you put a whole bunch of resistors in series, that is similar to just having a longer resistor. That's going to increase the resistance. And that means that I can just add them like regular numbers. But if I put resistors in parallel, that is similar instead to increasing the cross-sectional area. It's like making it wider. The cross-sectional area is in the denominator. So when I do that, the resistance needs to go down. And consequently, parallel resistors are added in that same reciprocal style that you saw with capacitors, except with capacitors everything was backwards from this. So series resistors added normally. With capacitors, it was parallel capacitors that were added normally. Resistors in parallel are added by reciprocals, whereas capacitors in parallel were added normally. The reason for these differences is basically the location of the A versus the location of the L or the D. So that's, if you can't just remember the addition rules, these two formulas, they are on the AP formula sheet. So you can use those rules to remind you, you can use those equations to remind you how to add the different objects. And that is it for this section. I'm going to make another shorter video about other stuff, which I'll probably post at the same time, but that's it for this one.